Let's go ahead and take some time to review statically indeterminate axial bars. We went over a lot of the content last time. You're getting a chance to practice that. And this really weaves together so much of what we've done so far. So for all statically indeterminate problems, remember that we use what are the big three or the three tools of structural mechanics. Some people would say structural analysis, any of those sorts of phrases. But we'll say the three tools of solid mechanics. And as we indicated last time, the first is going to be statics. And the word that goes along with that is equilibrium. You can use either one of those. They mean the same thing. So don't think that you have to use one or the other and I'll count you off. But it means that the deformed structure has to satisfy equilibrium. The problem is, of course, that that's not going to be enough. The second tool is going to be the constitutive law or the stress-strain law. So we abbreviate it like that. Now, the nice thing about that is, by the way, if we had another phrasing that we would use, is we would say something like material properties. In other words, sigma has to be equal the modulus elasticity times the normal strain for the axial bar. But what we found was that means that delta is going to be equal to PL over AE. We're assuming that we're only going to be studying statically indeterminate problems that have a constant P, A, and E. So, constitutive law, the deformed solid has to conform to known material properties. Then the third one is compatibility. I'm going to abbreviate that. And the word that we use for that is geometry. In other words, the deformed geometry has to be geometrically admissible. There cannot be a gap. If you start with something that is a triangle and that is say a planar truss, which we won't have, but that's just an example, and then it deforms, it has to stay where the joints are all going to be connected. There's not going to be an opening up of a gap between something that was originally connected together. Now, those three are very, very important. Those are going to go way beyond this class. So they are very useful things for you to have committed to memory. Now, for the axial bar, which is, of course, our problem, the other good news is that there is a quantified number that you can commit to memory. So there are going to be three types of statically indeterminate axially loaded bar problems. The first one is the fixed. So it's going to have something that looks like this. There's going to be a fixed support. Now, I suppose I could do this. And then you've got something, a collection of bars, one or two or more, something that looks like this. Or it might look like this, what have you, and you've got some loads on it. There might be a load here, there might be a load here. But each section of the material could possibly have different values of P, A, and E. That was a little bit sloppy. And then notice even this is going up and down. You can reorient it so that it's going this way. Now remember, a couple of hints on this. For this sort of problem, my suggestion is always take the left support and draw the reaction going to the left. So let's just call that R at the left-hand end. And the reason for that is that makes the interior statics calculation very easy. So for the first segment, if you make a cut there, you'll always have P1 is equal to the reaction. And then you make the second one, you make the third one. So a couple of kind of key phrases on this. Let's make some bullets. First off, there are two applications of statics. The first type is the global statement of equilibrium, because not only do you have R at the left-hand end, you've got the reaction at the right-hand end as well. But the more important one is going to be the internal bar forces. And you need to have those. So you're going to have to make a sequence of cuts like we've done here. 1 cut, 2 cuts, 3 cuts. You're going to have to make a sequence of those to get the internal bar force. Then you apply the stretch in each segment. So we'll get the delta in each segment. And then here's the other big bullet, the statement of compatibility. Always for the fixed. By the way, I don't think I ever labeled this. This is the fixed fixed bar. The statement of compatibility is always going to be the total stretch is 0. And in this case, there would be 3 segments, so we would have delta 1 plus the stretch in bar 2 plus the stretch in bar 3. Those are all going to be equal to 0. So this is a given for the fixed problem. You just add up all the internal bar stretches, set that thing equal to 0. So each of these 3 types of statically indeterminate axially loaded bars has a very distinct character. And it's a very comforting bit of knowledge that you can kind of isolate what the statement of compatibility is going to look like for all of those particular cases. So again, that is the fixed bar. That's our first type of statically indeterminate axial bar. The second is the composite. Now we did a example with 4 pieces of rebar. Let's set up a different one now. Let's say that we've got 2 different materials looking like this, like so. So that would be our material number 1. That would be our material number 2. And let's say it's brass. So 1, let's say, is brass. 2, let's say, is steel. And we've got a force coming down like this. So part of that axial force is going to go into the brass. Part of it is going to go into the steel. And you don't know. You can't just divide it however you would like it. You have to use a formalized process to do that. So let's bullet the key items as they relate to our 3 major tools of structural mechanics or solid mechanics. First is that the statics is easy. You don't have to draw a free body diagram in this case. So we'll say no free body diagram. Now I suppose you could if you wanted to, but it would probably not be the best use of your time, because it's basically saying that the applied load is balanced by the force in the first material plus the force in the second material. Now remember that in the case of the rebar reinforced concrete, we had 4 bars. So there it would have been P of the concrete plus 4 force of the steel. So you have to count up the number of bars that are in there, or the number of rods, or the number of elements that are in there. But almost always that's going to be a pretty easy / trivial calculation to make. So now that we've got the statics part, the stress-strain law appears as it normally would. So that's going to be delta 1 is equal to P1 L1 over A1 E1, and that delta 2 is equal to P2 L2 over A2 E2. Now in this case, the case of the composite bar, almost always the length is the same. So L1 is L2 is just going to be that total length. The second thing that we've got to watch for a little bit, watch out for A2. A2 is hollow. You have to subtract the interior area of material number 1. So make sure that you subtract area 1 from the circle. So it's not going to be correct. So A2, let's draw it like this. That's A2, which is equal to this entire area minus A1. So that is a common mistake to make. Make sure that you change the area. You've got to adjust it to account for that. Otherwise, you could have pretty significant errors if you do that. Or pardon me, if you don't do that. Then finally, the statement of compatibility. Again, you can commit this to memory. It's always going to be the same for composites. And that is that the deflection is the same in both materials. So you have delta 1 is equal to delta 2. So that is always going to be your statement of compatibility for this class of axially loaded bars. Now the algebra on this one gets a little bit messier, I suppose, because you have to take this value, it goes here. You have to take this value, it's going to go into here. So normally what you would do is you would cancel the L's, and then you would solve for P1 in terms of something times P2, and then that goes back into statics. So then you're going to have P is equal to P1 plus P2. So you would replace that. So you're going to have something times P2 plus the original P2, and you solve for that particular force. So you're going to get P2, then you can get P1, and then you can use either of those to solve for the stresses. You can get the sigma 1 is equal to the P1 over the A1. Sigma 2 is P2 divided by A2. And you can use either delta 1 or delta 2 to get the total bar force. Whatever one is going to be easier for you. So that is our second type of problem. That's number 2, the composite. The third is the rigid link. And again, they'll always appear either something like, this. The rigid link will typically look like an L with some sort of pivot point. And that's not the axial bar. The axial bar might be there, and there might be one here. Like that. Like so. Or it could be something like this. It might be straight. And you have a bar there, so there's the hinge, and you've got a elastic bar there that resists the load, and maybe one here that resists the load. A couple of keys on this, almost always on the statics, it's going to be a moment equation. You're going to sum the moments about some hinge. So that's going to be here, or it's going to be here, because you want to get rid, I should say is equal to 0. So you want no reaction forces at that hinge. So the way to eliminate that is to sum moments about that point. The second key is draw the deflected shape. Draw the deflected shape, and the forces resist the movement. The forces are going to resist the movement. In other words, if I draw the deflected shape and it moves like this, like so, then the axial bar forces are going to go that way against the motion. It's going to go that way against. If I assume my movement is this way, by the way, I guess I should put a load here and a load here. Then it's going to resist the movement this way. It's going to resist, it's going to resist the movement this way. We'll come back to this one after we've done, or pardon me, I should say during part C. That's it for part B.